Hi, and welcome to this recording for Unit 60. Unit 60 talks about basically an overview of how stars evolve. You will notice that it's going to depend on a critical parameter, namely their size, their mass, basically. Okay, so we're going to describe the phases through which a star goes through based on theory and observation, and also explain the recycling of matter, because as the star basically sheds its outer layers, that becomes a ingredients for the next generation stars, basically. And then we're going to sketch and see how the star evolves depending on its mass. If it's a low mass star, there is a path, and if it's a high mass star, there is a different path. So, how do we know what we know? Again, stars evolve like human beings. Basically, they go through stages until they run out of their fuel, and then they basically go through toward the end, the final stages of their lives. How do we know that? First of all, we don't live long enough to see one star, even the high mass stars that go very fast through their lifespan, to witness one evolution. So what we have in here, if we take a picture of the sky, we will see stars at different stages of their life, basically from a protostar all the way to either a black hole or a neutron star or a white dwarf. So that's basically the idea. It's like, and this is a typical example, the classical example. It's like an alien basically passing through Earth, taking a picture in a fraction of a second, basically, of all the humans. He or she will see basically humans at different stages of their lives, basically from babies being conceived all the way to the conception, probably the birth of a child, and then all the way to probably the death of that human being. Based on that picture, that alien will construct a lifespan of a human being based on just one picture. That's what we have. The other thing also, we have numerical simulations, basically on a computer. We model how the star will evolve, and we will see predictions based on that models, and we go outside and we look at those predictions and we see a fit. Sometimes we adjust the models based on our observations, but that's the idea behind it. So this is what we know. We know that there are two, for every star, two competing forces. Gravity wants to collapse the star on itself. That's because gravity attracts everything, okay? And then you have heat, temperature inside, heat that wants to be released, that will build the pressure in the opposite direction where the gravity is acting. These two, when they balance, we have a star that is held together by these two forces, and this is called the hydrostatic equilibrium. So we have gravity and pressure. Okay. Well, this is for a normal, basically where is that energy is coming from? It's coming from the core. So the heat is released from the surface, and it's replaced by the heat that is generated inside the core based on the nuclear reactions. Granted, a star that is big will have more gravity trying to collapse on itself. So in this case, you really need more heat to maintain that balance. So you need a faster nuclear reactions in the core than what a low mass star is. Because a low mass star, you don't need as much heat to balance the gravity. Whereas for a big, massive star, it wants to collapse on itself because of the gravity, so you need more heat to maintain that equilibrium. Which means that a high, massive star will go through its material much faster than a low mass star. Now, a low mass star will end up in a white dwarf because it doesn't have enough gravity to overcome the forces of basically that keep different materials together. And in this case, it's the electron degeneracy. The reason why I'm sitting on a chair right now is because my body is pressing on the chair, and the chair is pressing back. And that is because of the electrons. They really don't want to press to go further than a certain distance. Like for example, right now my hands are pushed together, and the reason why is because the electrons on one side of my hand and the electrons from the other side of my other hand, they're interacting with one another. This is basically, I don't have enough pressure to cause electron degeneracy. As a matter of fact, there's an electrostatic force that's even less than that, but it's similar in the idea, okay? Now, if there is more mass, basically, this is the idea for neutron stars, those electrons will be pushed into the nucleus, forcing them to basically fuse with the protons and convert it to neutrons. So for more massive stars, they could become neutron stars. And for even more massive stars, the neutron degeneracy, which is in this case prevents further collapse of the star from in the neutron stage, to even collapse more if there is more material, okay, to become a black hole. So that's basically the idea behind it. So the low mass star will turn out into a white dwarf when it runs out of heat in its core to sustain that pressure. And a high mass star, depending on how high that is, either could end up in a neutron star if it's not that high, or if it's higher than that, it's actually going to collapse into a black hole. So this is the idea behind it. Okay. So star starts from few light years span of interstellar cloud, mainly hydrogen and helium and some basically low quantity of the other higher materials, okay? So now, due to the force of gravity, that material starts to come to coalesce together, and then we have a protostar. At this point, it's still not a star yet. It's hot, but it's because converting potential energy into kinetic energy. It's gravitational potential energy into kinetic energy, energy of motion. But at some point, that heat will be high enough so that it starts fusing hydrogen. And in doing so, it's going to expel a lot of that, shed a lot of that interstellar cloud and become a star. So at this point, it's fusing. So we're talking about a low mass star in this case, like the sun. So in this case, it's fusing hydrogen in its core. At some point, it's going to run out of hydrogen in its core, and it's going to swell because in this case, the collapse will increase with gravity. Now there is nothing to oppose it, so the core starts to collapse, increasing its temperature, which means it's going to push the materials way outside. That lowers its temperature, but it becomes a red giant, okay? The outer shells in this case. It's going to swell to about 30 times its original size. At some point, the temperature will be high enough that and it's in this case it's still burning hydrogen. It's hot enough for hydrogen, but not inside the core. It's actually in the shell. At some point, the temperature will become so high because that's not enough. So the collapse continues until the temperature reaches high enough temperatures that in this case you have helium that is fusing. And in doing so, it's going to be forming carbon and basically oxygen and some of these materials. And then it's going to run out of that again. It's going to go to the next shell and swells again. At some point, it's going to shed all of its outer layers and the core remains exposed. There is no more fuel, nuclear fuel, inside the core of the star that keeps it basically burning anything. So in this case, it's going to become a hot white dwarf that is going to start to cool down. Remember, the core, its temperature is in the millions of Kelvin, but at this point, its temperature drops drastically to probably several, maybe about 40,000 Kelvin. But at that point, it's still super hot. But that temperature is not going to be sustained anymore. I mean, there is no source of heat anymore. So that heat is going to be released, and the star will evolve into a white dwarf. So what happened to the material that sheds? That's a lot of material. That again will coalesce with other materials probably, or even by itself, with the existing clouds, the interstellar cloud, or itself by itself, and then repeats the process again. Okay, so this is a low mass star. A high mass star on the opposite side, again, it starts similar. Granted, it has more materials to start with, so it's going to collect more material to begin with. It's going to go through the protostar stage, ejects all of the materials, but now it has more mass to begin with, so it needs to have hotter surface temperature because it needs to maintain that pressure. So it needs to have a high rate of nuclear reactions into its core, goes fast through it, Then at that point, after that, it's going to go through its hydrogen, and then the process accelerates super fast and continues to burn more and more because there is room for increasing temperature far past the temperature for nuclear fusion for helium. So in this case, it's going to start to fuse heavier and heavier elements up until it reaches iron. And at that point, there is no advantage from fusing high iron. As a matter of fact, iron is an energetic nuclear reaction, means it requires more energy than it's going to give off. So in this case, the star will collapse on itself because it doesn't have that source to fuse elements past the iron. So in this case, it's going to collapse on itself, and it's going to end up either in a neutron star. Remember, this is a high mass star. So it's going to be either a neutron star, or even if it's more massive, it's going to be either a black hole. Okay. The clouds again will coalesce again to form the cycle again. So that's because this is going to be a supernova. And the supernova again will feed the interstellar cloud to form new stars. Depending, again, if it's a high mass star, it's going to have a similar path. If it's a low mass star that's going to form again, it's going to go like the previous slide. So this is in summary, basically what we have, except that there is something in here that could end up if we have a binary and one of them go through this stage. The white dwarf that forms, or the neutron star that forms, has a possibility on feeding of its partner. In doing so, it can grow, and then the process repeats again. So it can glow at least for a moment, and then go probably a supernova or something like that. Okay, obviously it doesn't happen if it's in a black hole. So again, this is a path. So we have a gas cloud. It's a good idea to start from the interstellar cloud. Then the gravitational contraction, converting gravitational energy into kinetic energy. Star heats up, then goes through a main stage star, whether it's going to be a low mass or a high mass. If it's a low mass, if it's a high mass, it's going to go through its material much faster than a low mass. Then it's going to swell at some point and become a red giant. Then it's going to go supernova or a white dwarf. The clouds again that are ejected are going to feed the interstellar cloud and repeat the process again. And then the heating will cool depending on one of the scenarios. A white dwarf usually is much bigger than a neutron star, which is bigger than a black hole for the same starting points of mass, or roughly the same size of mass. Anyway, so these two, they could end up going back through this stage if they're part of a binary. Okay? How a star evolved depending on how much mass it starts on the HR diagram. So if it's a low mass star, it starts as a protostar. Again, this is the gravitational energy being converted into kinetic energy, and the protostar heats up. At some point, the temperature becomes so high enough so that the nuclear reactions are triggered. In doing so, it's going to eject most of the gas that surround it. That fed the planetary formations, actually. Sorry about the cat. And at that point, once the nuclear reactions start, the star evolves into inside the main sequence diagram. Pattern. In this case, later on, because of the fact that it's consuming more and more of its energy, so it's going to heat up and swell a little, and then when it runs out of its hydrogen inside the core, then it's going to go through several stages of actually burning hydrogen in the shell, and then helium, and then after that, it's going to cool down and become a white dwarf. The protostar, though, on the other hand, for the high mass star, will evolve again a little bit slower initially and gather more material in doing so and become more massive and go through its main sequence stage again. And then after that, it's going to become a red giant, and then it's going to go quickly in its stages in here and go through a supernova stage where it's going to end up either as a white dwarf or as a neutron star or a black hole. Okay. A key point in here, and sometimes some of my students are actually confused about this one. This is not a physical motion. The star is not moving in space like that, okay? The star could be in the same location. Granted, it's probably part of a system that evolves around the galaxy somewhere. And in that same location is going through all of the stages. So this is not a physical motion of the star. This is actually an evolution in the same spot. Granted, that's probably moving around the center of the galaxy. Thank you.